The periodic table is a map of chemical behavior. Whether we are extracting lithium for batteries or using chlorine to treat water systems here in Uganda, an element's position on this grid reveals its physical and chemical properties. To read this map, we look at a microscopic tug-of-war happening inside the atom. On the left is the nuclear charge, the positive protons pulling electrons inward. On the right is the shielding effect, the inner electron shells acting as physical barriers that block that central pull. This tug-of-war is the engine behind every trend we see. Identifying which force is stronger in a specific element helps us understand why some are highly stable, while others are incredibly reactive. We see this first in the horizontal rows, or periods. As you move from left to right, you add more protons to the nucleus, which increases that inward positive pull. Watch the progression across period 3, from sodium to magnesium to chlorine. Though we add more particles, the physical atom actually shrinks. Because new electrons are added to the same outer layer, they provide no new shielding. The growing nuclear charge pulls the structure tighter, making the atom smaller. This is why atomic radius always decreases across a period. The nuclear pull simply overpowers the shielding effect. Down a vertical group, the math changes. You are adding entirely new layers of electron shells, which physically expands the atom's size. This size increase determines the ionization energy, the energy price required to strip an outermost electron away from the atom's grip. Imagine the nucleus as a magnet and the outer electron as an iron bead. The thick inner electron shells act as a shield. The more layers of shielding you add, the weaker the magnet's grip becomes. The further the electron is from the center, the easier it is to remove. This means moving down a group decreases ionization energy. The expanding shielding effect effectively blocks the nuclear pull. This shielding explains why reactivity changes differently for different groups. Group 1 metals want to lose an electron, while Group 7 nonmetals want to gain one. In Group 1, heavy shielding makes elements like cesium highly reactive. Since the nucleus barely holds the outer electron, the atom easily ditches it. But in Group 7, thick shielding makes it harder for a large atom like iodine to pull in an electron. Small fluorine, however, has little shielding and snaps up an electron instantly. Let's test that logic. Look at potassium and sodium. Based on the shielding effect, which one has a lower ionization energy? Potassium has the lower ionization energy. Because it is lower in the group, it has more shielding layers weakening the nuclear grip. We can apply this to a standard UNEB-style examination question. Which of these elements has the largest atomic radius? Lithium, sodium, potassium, or rubidium? As we move down Group 1, we are adding a new electron shell at each step. This adds a new layer of shielding and increases the physical distance from the nucleus. Because it has the most shells, rubidium is the largest of the 4. These trends create a clear pattern. Elements at the bottom left are large reactive metals. Elements at the top right are small, reactive nonmetals. Balancing the nuclear pull against the shielding effect provides a framework for understanding chemical behavior. It allows you to anticipate the properties of an element simply by looking at its position on the map. For more step-by-step lessons and exam practice across all classes, visit us at Yaka Digital Network.